Okay, we're on the equilibrium constant, and we're going to skip the warm-up. Let's take a look at deriving the equilibrium expression. If you've got a reversible reaction, hydrogen gas combines with iodine gas to produce 2 hydrogen iodide. The forward and reverse reaction rates are given by the rate of the forward reaction equals constant K for the forward reaction times the hydrogen concentration times the iodine concentration. And then the reverse reaction is given by the reverse constant K times hydrogen iodide raised to the second power because its coefficient is a 2. And at equilibrium, you know that the forward reaction equals the reverse reaction. And if you set up this equation to this equation, when the forward reaction equals the reverse reaction, and you rearrange to get the constants alone, then you will end up with something we call the equilibrium constant Keq. So the ratio of the forward and the reverse reaction constants is going to be Keq. This is equal to the concentration of your product over the concentration of your reactants. And the powers on the concentrations are equal to the coefficients in the balanced chemical equation. And the rate constants for the forward reaction and the reverse reaction are temperature dependent. So that means that the equilibrium constant Keq is as well. So the equilibrium expression is referring to the formula for the equilibrium constant in terms of the equilibrium concentrations for the reactants and the product. So this right here is your equilibrium expression, the concentration of your product, so the concentration of your reactants, and it's raised to the power of the coefficients. And the equilibrium constant is referring to the numerical value that's provided by this equilibrium expression. So after you substitute in your concentrations at equilibrium, you're going to get the equilibrium constant Keq, and it will not have a unit. If you take a look at the next page, at the practice problems, here, number 1 says that you have these gases at equilibrium at 423 degrees Celsius. They give you the concentrations. What's the equilibrium constant for the reaction at this temperature? So Keq is going to be equal to the hydrogen concentration times the iodine concentration divided by hydrogen iodide raised to the second power because that's its coefficient. We're going to substitute these values in. So it's 4.56 times 10 to the negative third times 7.4 times 10 to the negative fourth divided by 1.35 times 10 to the negative second squared. You're going to end up getting 0.019. Now if we're doing number 2A, we've got this concentration of NO2, this concentration of N2O4 at 60 degrees Celsius. They want the equilibrium constant. So this is going to be equal to 1.73 times 10 to the negative fourth, because that's the concentration of N2O4, over the concentration of NO2, which is 3.88 times 10 to the negative third. And since there's a coefficient of 2 in front of NO2, you'll put it here. You're going to end up getting 11.5 for your Keq at that temperature. B says, state whether this reaction is endothermic or exothermic by comparing the equilibrium constant at 60 degrees with the equilibrium constant at 92 provided in the previous sample problem. Okay, so if my Keq is 11.5 at 60 degrees Celsius, and I look back at the previous sample problem, which says that the Keq is 4.4 at 92 degrees Celsius. This is a higher temperature with a lower Keq. Now, Keq is a ratio of the product concentration over the reactant concentration. So what that means is At a lower temperature here, it looks like we have more product than reactant because your KEQ value is higher than it is at 92 degrees Celsius. So down here, that means we must have more reactant than product at a higher temperature. Now, there are two different types of reactions. There's endothermic and exothermic reactions. And if you have an endothermic reaction, that means you have heat as a reactant. And if it's exothermic, you have heat as a product. So, if you increase the temperature, which is what they did here from 60 to 92 degrees Celsius, of an endothermic reaction, you're going to shift to the right and you're going to increase the concentration of product. So this must not be an endothermic reaction because I have more product at the higher temperature. Whereas here, if you increase the temperature of an exothermic reaction, I'm increasing product, so I'm going to shift to the left. And when you shift to the left, you're going to increase the reactant concentration, which is what happened here. So that means that this is an exothermic reaction. Let's take a look at number 3. Number 3 asks us to solve for the equilibrium concentration of H2 given the concentration of NH3 and the concentration of N2 at equilibrium, and they gave us the KEQ value. So you know that KEQ is equal to the concentration of your product raised to the second power because of the coefficient over the concentration of your reactants, and then H2 has a coefficient of 3, so that's my exponent. So we're going to put 1.7 in for KEQ times 10 to the second. This equals my NH3 concentration raised to the second power over the concentration of N2, which is 0.020, times the concentration of H2 cubed. If you multiply both sides by 0.020 times H2 cubed, this cancels here, and you're going to get 0.020 times 1.7 times 10 to the second times H2 cubed equals this. You're going to divide both sides by 0.02 and 1.7 times 10 to the second, so these are canceling. Then you're going to solve for the concentration of H2. Whatever this is, you have to raise it to the 1/3 power so you can cancel out, since it's the cubed root, the exponent on H2. And then you're going to end up with 0.18 molarity for the concentration of H2. Now, the size of the equilibrium constant is telling you the extent of the reaction's progress towards products. And the further a reaction progresses to the right to achieve equilibrium, the greater your equilibrium constant will be. And there's a couple of things that we have to mention here. You really can't infer anything about an equilibrium's position solely from its equilibrium constant. An equilibrium's position depends on the initial reactant concentrations and the equilibrium constant itself. So if I'm looking at this equilibrium reaction here. I've got acetic acid in equilibrium with its hydrogen ions and acetate ions. Its value for KEQ is 1.8 times 10 to the negative fifth. If the initial concentration of acetic acid is 1 molar, there will be a 0.42% yield at equilibrium. That means that I am further to the left. But if this initial concentration is 1 times 10 to the negative 6, then I have a 95% yield at equilibrium, which means I'm further to the right. So diluting it, which means I'm adding more water, causes a shift to the right because I want to restore osmotic pressure based upon Le Chatelier's principle. Down here, if I'm looking at two different equilibria, which I have here, and I have the same initial reactant concentrations, I can't make a meaningful comparison between these equilibrium constants, even though they have the same value of 1, because these two are going to have different percent yields, even if they have the same equilibrium constant at different temperatures. If you're comparing identical equilibria and we're at 2 different temperatures, that's another thing. But you can't compare 2 different equilibria. Let's take a look here. Does an equilibrium constant change when the equilibrium system shifts? The only way you're going to change the equilibrium constant is if you change temperature, and I'll show you why. Here in this reaction, if I add reactant, I may shift to the right, but I will see no change in the equilibrium constant. If I decrease the volume, you're going to end up shifting to the right to bring the pressure down, but you will see no change in the equilibrium constant. If I change the temperature, however, I'm going to see an increase in the equilibrium constant. So this is showing you that temperature changes affect the equilibrium constant. If you turn to the next page, take a look at the quick check. Consider the following equilibrium. In what direction will the system shift if some ammonia is added? So if you add ammonia, you're increasing the concentration of reactant, so you should logically shift to the right. How will this affect the equilibrium constant? Well, it won't. There's no change, because a change in concentrations will not change your equilibrium constant. Number 2, consider the following equilibrium. A decrease in temperature will cause the equilibrium system to shift in which direction? Well, here you've got energy going in as a reactant, so this is an endothermic process. So if you decrease the temperature of an endothermic process, you're decreasing the heat, which is a reactant, which means you're going to end up shifting left. And that causes your percent yield to decrease because now you're further to the left where the reactants are. You're not going to have as much product. And that means that your equilibrium constant is going to decrease because your equilibrium constant is affected by temperature changes. And it's a ratio of product over reactant. Number 3, consider the following equilibrium. Your KEQ value is 0.36. True or false? We know that reactants are favored in this reaction because KEQ is less than 1. We don't know that. So this is false. We can't deduce that. If you take a look down here where it says no liquids or solids in equilibrium expression, we do not include anything that has a state of matter as a solid or liquid. So if you're looking at this reaction here, we would exclude NaCl because it's a solid. Your equilibrium expression would be the concentration of sodium ions times the concentration of chloride ions only. If we're looking down here, I have 3 substances dissolved in water and I have liquid water. We would exclude liquid water from our equilibrium expression. Okay, water is just a solvent and its concentration is nearly constant, so that's why we're going to omit it from equilibrium expressions. If you take a look at the next page, it says write the equilibrium expression for the following reactions. So in this first one, we would exclude the solid. So this would be water raised to the third power, because it's a gas, so we would include it, divided by V2H6 times O2 raised to the third power. For number 2, we would include all of these. So this is Cl2 squared times H2O squared, because H2O is a gas, divided by HCl times, or raised to the fourth power, times O2. And then at number 3, we would exclude liquid bromine. And then at number 4, you would exclude the calcium carbonate because it's a solid. The next section, the equilibrium constant and the form of the chemical equation. If you have a reaction, given here, hydrogen gas combines with oxygen gas to make water, your coefficients are 1, 1/2, and 1. The equilibrium constant value is 3. If I take this reaction and I multiply it by 2, I get 2, 1, 2 for the coefficients, and the KEQ value is now going to be squared. So if you multiply a reaction by 2, the KEQ will become squared. So that's how they get 9. 3 squared gives you 9. So doubling the coefficients squares its KEQ. If you take the same reaction and you reverse it, so now H2O is my reactant. What will happen to your KEQ is you will invert it. So here, this is the reverse of the reaction that was up above given first. And your KEQ now is 1 over, because originally the KEQ value was 3, and they just took it as 1 over 3 gives you 0.333 if you reverse it. So if you reverse the equation, you will invert your KEQ. If you take a look at the quick check here at the bottom, they give you this overall reaction. 2HI produces an H2 and an I2, and your KEQ is 0.018. At the same temperature, they reverse the order and put these products as reactants and this reactant as a product. So you will take 1 over your KEQ. So 1 over 0.018 is going to be 56. Number 2, what is the KEQ at the same temperature of this reaction that they divided by 2? So we went from 211 to 1, 1/2, 1/2. You're going to take the square root of KEQ. So this is going to be the square root of 0.018, which is 0.134. And number 3, what is the KEQ at the same temperature? And they took this reaction in number 2 and they reversed it. So that means you're going to take your KEQ from the previous problem and do 1 over 0.134, which is 7.5. Okay, on the next page, we talk about the reaction quotient. The numerical value that's derived with any set of reactant and product concentrations is plugged into an equilibrium expression, and it's going to give you something called the trial KEQ, which is the same thing as the reaction quotient Q. So think of it as this is just a trial run. We're going to calculate the trial KEQ, and we're going to compare it to the actual KEQ. So if your trial KEQ is less than the actual KEQ, then the reaction has to proceed to the right to achieve equilibrium. If the trial KEQ is greater than the actual KEQ, then the reaction must proceed to the left to achieve equilibrium. Okay? If you take a look at the next set of practice problems here, we're given this reaction. We have the KEQ value, so this is your actual KEQ. And they gave you concentrations to calculate our trial KEQ. So your trial KEQ is equal to carbon monoxide, which is 0.10, times H2, which is 0.30, raised to the third power, all over CH4, which is 0.025, times H2O gas, which is 0.045. You're going to end up getting 2.4. So my trial KEQ is 2.4, and my actual KEQ is 4.7. Well, this is less than that. So when your trial is less than the actual, the reaction proceeds to the right to achieve equilibrium. Okay. If you take a look at number 2, they give you a 0.5 liter flask with this many moles of reactant and product in it. They want to know in which direction we proceed to achieve equilibrium with this actual KEQ value. So your trial KEQ is equal to the concentration of N2O4, this is in moles per liter, so you have to divide it by 0.5 liters, all over 1.5 moles of NO2 divided by 0.5 liters, and then you would raise this to the second power because of the coefficient of 2 in front of NO2. This is going to end up being 0.89. So your trial KEQ of 0.89 is less than the actual KEQ of 0.940. So this is your trial, this is your actual. So that means you will also proceed to the right to achieve equilibrium. Take a look at number 3. Number 3 says, in a container, 0.1 molar H plus and 0.1 molar SO4 exist in equilibrium with 0.83 molar HSO4. A buffer is added to increase the concentration of both bisulfate and sulfate. So this is bisulfate, and this is your sulfate, by 0.1 molarity. What happens to the HSO4 concentration as equilibrium is restored? Okay, so KEQ is equal to the H plus concentration here times the SO4 concentration here all over the HSO4 concentration on the bottom. So this is going to end up being 0.10 times 0.10 divided by 0.83, and this is 0.012. Then so these are the concentrations that I put in here. Okay, so this was at equilibrium. Now, if we change the concentrations, let's look at our trial now. So this is going to end up being, they changed the concentration of bisulfate and sulfate, so these two. So your H plus stays the same. So we're going to do 0.10 for our H plus concentration. And then the other one is going to be 0.20 because it increased by 0.1. And then your HSO4 concentration increased by 1, so that's going to end up being 0.93. So this equals 0.022 for your trial KEQ. So 0.022 is greater than 0.012. So your trial KEQ is greater than your actual KEQ, which means you're going to shift to the left to restore equilibrium. And if you shift to the left, the concentration of HSO4 is going to increase. All right, so let's talk about the addendum to Le Chatelier's principle. And let's do that just by looking at the next page. I'll just explain it here. When you're looking at equilibria that have only one chemical concentration in their equilibrium expression, they have to completely alleviate any stress that changes that concentration. So if I'm looking at this example here, water evaporating and condensing. I have to cross out the liquid water. I cannot include it in my equilibrium expression. So that means that you only have one substance to consider in your equilibrium expression. Same goes for this example. Calcium carbonate is a solid. It's going to decompose into calcium oxide solid. I only have carbon dioxide gas. So for my equilibrium expression, I'm only concerned with the concentration of carbon dioxide. So these equilibrium expressions have one chemical concentration in them. And if I end up with an entire loss of that substance in the equilibrium expression, you have to restore the reaction quotient back to what it was at the equilibrium constant. So if you're taking a look at the quick check down here, and I want you to state whether each of the following will partially or completely alleviate a stress that changes a reactant or product's concentration. If you take a look at number 1, we have cobalt 2 chloride solid. That's out, and then my product is a solid. That's out. So that means my KEQ is 1 over water vapor raised to the 6th power. Well, I'm going to have to completely alleviate the stress because I only have one substance in my KEQ expression. For number 2, ammonium chloride is a solid. I have 2 gases. So my KEQ expression is going to be NH3 times HCl. That means I will partially alleviate the stress because I have more than one substance in my equilibrium expression. For number 3, I have 2 solids, leaving me with one substance in my equilibrium expression, which is 1 over CO2. So that means I will have to completely alleviate whatever stress changes that concentration.